Okay, so this is actually where we get into our function notation. How can we write an inverse function using the function notation? And then, of course, we'll talk about how to find inverses. So just as a quick example here, we're actually going back to our pizza example that we looked at in the beginning of this section, which is where they told us if you get a plain cheese pizza, you're paying $5 for it, and then for any additional toppings, you would end up paying $2 each. Now, when we inverted our function, or basically switched our x and y values, this is where your x now became the number of toppings and y became the cost of the pizza, whereas in the original, the x represents the cost and y was the number of toppings. So that's actually the function that we're going with here. So this is where your x is actually representing the cost in this case right now. So it's $5 for the plain cheese pizza and $2 for any additional toppings. Sorry, this is the cost. That's the number of toppings for the x value. So how do you find the inverse? You know, going from 2x plus 5 to changing our x and y values. So you actually start out by literally interchanging your x and y variables here. So the first thing you'll notice is instead of writing it as f of x, we're actually replacing our f of x with y. You've got y equals 2x plus 5, and this is where we interchange the places of the x and y variables. So instead of having y equals, you now have x equals, and then instead of 2x, that one will become 2y plus 5. So you're literally just switching the places where you write the x and y values at. And the idea is to try and isolate this y now. So once you make this interchange, bring the 5 to the other side, which will become x minus 5. And then to get the y by itself, we'll go ahead and divide by 2. And that's where I'm getting x minus 5, the entire thing divided by 2 equals y. Once you get this y by itself, you can actually replace it with the inverse notation, which is the f inverse symbol here. So in the original function, the x represents the number of toppings and the y, or the f of x, is the cost of the pizza. When I make that switch happen, when I get my inverse function, the x here is actually representing the cost that you're going to pay, and the f of x, or the f inverse, is representing how many toppings you have. So if you think about this, let's say we go with 2 toppings here. So that'll be 2 times 2, which is 4. 4 plus 5, which will be 9, right? So that means we're going to end up paying $9 for this pizza. So in the inverse function, if I start by putting that 9 in here for my x value, 9 minus 5 is 4. 4 divided by 2 is 2, which is telling me we got 2 additional toppings on our pizza. So that's how the relationship between the original function and the inverse function should always work out to be. And they're actually using here an example showing you with 3 toppings instead of 2. So if we did 3 toppings, we'll end up paying $11 for that pizza. If I put that $11 inside my inverse function, it should come back showing me that we got 3 additional toppings. And remember, we had done these examples in the first part of this handout where we said the number that you start out with is the number that you end up getting when you do a composition between your inverse function and the original function. So that's pretty much what's happening here. And then you've got your little illustration here. So remember, the domain of the original function will become the range of the inverse function. The range of the original function becomes the domain of the inverse. So keep that in mind. So let's get into formally finding our inverse functions here. So these are the steps that we actually just went through with that pizza example. Start by replacing your f of x notation with y. Then we're going to make our switch, our interchange between the x and y values, and then of course try to get the y by itself. Isolate that y. Once you get that y by itself, you can replace the y with the inverse notation, so f inverse of x. And this last part, number 5, they're saying check that the domain for the original will become the range for the inverse, and of course the range for the original is the domain for the inverse. So let's see how we can use this switch and solve method to find the inverse of our function here. This guy is number 12. Really? What is going on with this? I have no idea. Okay, so we are given f of x equals negative x minus 9. So the first thing we are going to do is replace our f of x with y. Okay, so that's the step 1, I guess, of our switch and solve method. Once you replace your f of x with y, now we're going to interchange our x and y variable. So that means x comes on the outside and the y goes on the inside of the function. So switching our x and y variables. Now the goal is to get this y by itself, which means start by getting rid of everything else. So what's the first step we do to isolate that y? Yeah, move the 9. So we'll start by adding the 9. So these guys will cancel out, giving us x plus 9 equals negative y. And then we definitely want to get rid of the negative on the y. So how can we accomplish that? Divide by negative 1. So we take each term and divide it by negative 1. We will have a positive y left behind. And what will the left-hand side become? X divided by negative 1 will become what?
Negative x.
Negative x. And then same thing, positive and negative will make it a minus 9. Once you get your y by itself, then the idea is, just replacing the y with the inverse notation. So f inverse of x. So let's just put it here. F inverse of x is going to be negative x minus 9. So what do we notice here in this example? It's the same thing, right? So the original function is actually its own inverse because we got the exact same function here. Now for the checking part where they said check and make sure that your domain and range are going to get interchanged, we can actually just check it with a number. So let's start with the original function and give me a number for x.
2.
2? Sure. So starting with the original function, we'll put 2 in for the x, which means I have negative 2 minus 9, which will be what? Negative 11, right? Now we're going to take this answer and put it inside of the inverse function. So that's this guy right here, f inverse, and I'm going to replace my x with negative 11. So that's negative x. Since x is also a negative number, I'm going to put it in parentheses. And then, of course, I've got my minus 9. So what will I get as my answer here? You are going to end up getting 2 because negative times negative will become positive. So you end up getting positive 11 minus 9, which will be 2. So you can see we started with that 2 and we should end with that 2. So that's how you know the domain for the original function becomes the range for the inverse function, and the range for the original function becomes the domain of the original function. So that's how you can check and see if that domain and range will interchange or not. So that's our process of using the switch and solve method to find the inverse function. Any question on number 12? Do you at least understand the process of how we need to go about doing this? Okay, so let's take a look at number 13 here. Not again, seriously? Okay. So we've got f of x equals x plus 3 over x minus 5. So again, first step, replace the f of x with y. So you will end up getting y equals x plus 3 over x minus 5. Then what do we do? Yeah, we interchange our x and y variables. So that means x will replace the y and y will replace the x. So you're actually going to end up getting y plus 3 over y minus 5. So since I have y in two different locations, that means I'm going to have to find a way to bring those two y's together so that we can isolate it. So the first step we're actually going to do is multiply both sides by our denominator, y minus 5, so that we can basically cancel these guys out. And you end up getting x times y minus 5 and just y plus 3 on the right, once we get rid of our denominator. What can I do on the left-hand side? Actually, technically distribute. Okay, so x times y minus 5 times x equals y plus 3. Now remember what I said, we need to get the y terms on the same side. So I've already got the xy here. I'm going to bring the single y to the left, and that means I'm actually going to take the 5x to the other side. So we can start by adding the 5x to the right. And bring the y to the left-hand side. Which will again give us xy minus y, 5x plus 3. So we've got our y terms on one side, we've got terms that don't have y on the other side. What should we do next?
Divide by x on the left.
No, you don't want to do that because you'll end up with a fraction, especially on this part where you have 3 over x, and that really is not going to help us a whole lot. What else can we do instead of dividing by x? Well, both my terms have a y in common. How would I do that?
So then it'd be y and then parentheses x minus 1.
Yeah, you factor out the common y. So instead of dividing by x, because what's happening if I divide by x, this guy will get rid of the x, but I would still have y over x here. I would have a 5 here. I would have an x over 3 up there. So like I said, we're not really going to make life easy if we do that. So it's better to factor out the common y, which means from the first term, I'm only left behind with the x, minus, since I took this y out, we need a placeholder, so we put a 1. So you get x minus 1. The right-hand side, of course, is still 5x plus 3. Yeah, now to get y by itself, you divide both sides by the parentheses, which will be x minus 1. Alrighty, very good. Oh, no. You know, they updated the license on this, and for some reason it's acting funny now. Okay. This is going to be our inverse function. So it looks a lot different than what the original function we started out with. So just replace your y with the inverse notation. So our original function was x plus 3 over x minus 5. And you can see its inverse function comes out to be 5x plus 3 divided by x minus 1. Okay, now we still need to check and make sure that our domain and range are going to interchange. So let's start with the original function. What can I use for my x value here and keep it small?
4.
Going to use 4? Okay, on the original function, we're using 4, so that will be 4 plus 3 on the numerator and 4 minus 5 on the denominator, which will give us what does it give us?
And then over -1.
Which will become
-7.
very good. So 4 plus 3 of course gives you 7. 4 minus 5 gives you -1. 7 divided by -1 will become -7. So we'll take the -7 and put it inside the inverse function now. And your inverse function of course is 5x plus 3 over x minus 1. So that's 5 times -7 plus 3 divided by -7 minus 1. What does that give us?
-35 plus 3 over -8.
Alrighty, so multiply 5 times -7, which gives you -35, plus the 3. Denominator, of course, will become -8. -35 plus 3?
-32.
-32, very nice. Divide by -8. You should come back to your +4. So again, started out with the 4, you should end with that 4 if we did our calculations correctly and we do indeed have the inverse function. So again, domain becomes the range becomes the domain for the original and the inverse functions. Okay. Questions on number 13? No? All right, let me see, bless you, let me see what you guys can do for number 14. Yeah, right next to the snacks,
Okay.
you'll see, I think it's underneath 2.4 saying that. So you've got cube root of x minus 9, and then plus 5 on the outside.
Is that how you say it?
You rearrange it.
Just kidding. I have to rearrange it.
Yes, that sounds like you
Have
need
a-
to
They
rearrange
have
it.
the right.
Okay, so what did it come out to be?
X minus 5 cubed plus 9.
Yes. All right, very good. Okay, so obviously replacing our f of x with y, then interchanging the x and y variables. I just saw a couple of you do this, but just be careful. You have to isolate the cube root before you can start using the third power, the cubed power, to get rid of it. So the first step should always be to isolate the radical, which means we'll move the 5 to the left-hand side. So we start by subtracting 5, and you've got x minus 5 equals cube root of y minus 9. Now, once you get to this stage, you can go ahead and get your cubed power in. So the cube and the cube root will cancel each other out. Leave this guy as it is. You don't need to multiply it or expand it out. Just leave it as x minus 5 to the third power. And on the right-hand side, since these guys canceled out, you're left with just y minus 9. Our goal is to get the y by itself, so obviously that means we need to add the 9 to both sides. These guys will cancel out. You end up getting x minus 5, the quantity to the third power, plus 9 equals y. Now, for checking, what number can we use in the original function? 7, okay.
Or sorry, 17.
17? Okay, so let's see. If we are going with 17, what else could we have used other than 17?
9.
Yeah, you could have actually used 9 itself. That would have also worked. But let's check it with 17 here. So 17 minus 9? 8. And what is cube root of 8? 2, because you're basically talking about what number multiplied into itself 3 times gives us 8, and of course that number comes out to be 2. 2 plus 5 gives us 7, right? Which means 7 is the number we're going to put in the inverse function. So for the inverse function, we have 7 minus 5, quantity cubed, plus 9. 7 minus 5 will be, of course, 2. Which should, of course, bring us back to the 17. If you use 9 as your original x value, what did you get as your answer?
5.
Yeah, 5. So 5 would bring you back to a 9. So if anybody used a 9, you should be able to verify that. All right, good job, guys. Let's see, this was the first one. There we go. Right, so that was how to use the switch and solve method to find the inverse of a function. So we're saying when two functions are defined by their formulas, it is not obvious whether the ordered pairs of one function are the reverse of the ordered pair of the other. And this here we're talking in terms of functions, right? We're saying we can use compositions of the functions to make the determination if you are basically looking at the reverse for your functions or not. So we had seen compositions when we did those first couple examples in this handout. Right here, when we did the composition, you saw that we ended up getting an identity pair, so we should have gotten 1, 1 for this guy. When we did the composition here, we got 2, 2 as our resulting ordered pair. So we always get an identity whenever we take the inverse and the function itself and do a composition between them. So that's what this little, and not again. So the composition here is telling us no matter which way you go in. So if you do g of f of x or you reverse that and do f of g of x, you should always get an identity function. Remember, your identity function is y equals x because all our ordered pairs are going to be the same numbers, 1, 1, 2, 2, 3, 3, -1, -2. I mean, -1, -1, -2, -2. So that's the idea. Instead of using specific numbers, if you actually just do a composition between them and your resulting answer comes out to be x, then we know for sure that the two functions are actually inverses of each other, which means the ordered pairs are definitely going to reverse in this case. So let's see if we can go ahead and check and see with this guy if we have inverse functions of each other or not. And you can see we have 2x plus 1, the other one is x minus 1 divided by 2. So what do we get with this? Number 15 f of x is defined as 2x plus 1. Now, instead of using f inverse, they're just using g of x as the notation. And ultimately, our goal is to show that these two are inverses of each other. So let's start out with the first composition, f of g of x. That means I'm taking the g function and I'm literally putting it inside of the f function. So your g is defined as x minus 1 over 2. So remember, in this case, when you are looking at composition, that means this entire value is going to replace the x in the f function. So when I do this little substitution, I will have 2 times x plus 1, but instead of x, you're going to replace it with x minus 1 over 2. And then our goal is, of course, to see how much can we simplify it. Do we actually get x as the only term left behind once we clean everything up? So here, we've got multiplied by 2, and of course, we're dividing that first term by 2. So both of these will actually end up canceling each other out, leaving us behind with x minus 1, and then we have that plus 1 on the outside. So what can we cancel out next?
The ones.
Yeah, the plus 1 and the minus 1, leaving us behind with dx. And this is what we wanted, because if this composition works, obviously things are looking good, but we still need to do the reverse order to make sure the other way is also going to give us an x value, and that's how we know these guys will be inverses of each other. So let's do g of f of x now. That means inside the g function, we're going to put 2x plus 1, which is coming from the f. So here, everywhere that I see an x is going to get replaced with 2x plus 1, which means we will have x minus 1 divided by 2, and the x is going to get replaced with 2x plus 1. Since I don't really have anything in front of the parentheses here, I can just write it without the parentheses, which will give me 2x plus 1 minus 1 at the end, and then everything divided by 2. So what's the first thing I can cancel out here? The ones, yeah. All right, very good. So plus 1 minus 1 cancels out. You're left behind with 2x over 2. Once you get rid of those ones, now stop doing that. We can cancel out our 2's, leaving us behind. Woo! That was very interesting. Leaving us behind with dx, okay? If you can show that going in both directions, f of g of x, the first part, and then g of f of x, in both directions I get x by itself, then we can say these are inverses of each other. Okay, so that's what we're looking for when we do this little process. So you can say they are inverse functions. Okay. Question on 15. Okay, so obviously I'm pretty much doing the same thing on 16, is trying to see the composition going in both directions and verifying if they are inverses of each other or not. Okay, so this time our f of x function is defined as cube root of x minus 2, the whole thing divided by 5, and then the g of x function is defined as 5x to the third plus 2. Okay, so we'll start with f of g of x again. So pretty much following the same steps that we did. That means inside of the f function, we're putting g, which is going to be 5x to the third plus 2. That means everywhere in the x function, we are going to replace it with the 5x to the third plus 2. So this will actually be cube root of 5x to the third plus 2. This is replacing our x. Then we have the minus 2 at the end. And the entire thing divided by 5. So this is actually very similar to what we just did, with the exception you have now a cube root on the top, which means again your plus 2 and minus 2 will cancel out first. You will then have just the 5x to the third divided by 5 left behind. Now that I have just the two terms, I can actually cancel out the 5's. And you can see at this point we have cube root with x to the third. Can I cancel those out? Yeah, because a cube cancels out a cube root, just like you guys saw in that previous example. And obviously, we end up getting just an x behind. So we know in one direction, these guys work well. The idea is, will they do the same thing? And hopefully, if it works in one direction, our hope is it will in the other. So go ahead and do the other way. And this guy will actually now be g, will be getting f as its inside function. So that's going to be cube root of x minus 2 divided by 5. So we're replacing our x in the g function with this whole thing. Take it slow. So you have 5 on the outside. We've got x to the third power and then plus 2. Now instead of x, we're replacing it with that whole cube root of x minus 2 over 5. What's the first thing that I can cancel out here?
Cubes.
Yeah, the cube root and the cube. Which has 5 on the outside. We just got rid of the cube root basically, so you still have x minus 2 over 5 left behind. What can we cancel next? Yep, the 5's. And that will, of course, leave us behind with x minus 2 from the parentheses, and you have the plus 2 on the outside. And obviously, your 2's will cancel out last, giving you the x. So as long as you can show going both directions that we are going to get x, we know these guys are inverse functions. Now, let's say you looked at an example where even the first part did not work out. You were not able to get x by itself. What would that tell us? They're not inverse functions, so that means you really don't have to worry about trying the other direction then, because if one direction is not working, it doesn't matter if the other direction works or not. So technically it shouldn't, because if f of g is not working, then g of f shouldn't. So if you get x on one side, we're really looking at a positive thing that the other side will work also. All right, any questions on 16? So this bottom part is telling us that obviously a function has to be one-to-one. You have to have that one-to-one correspondence for them to have an inverse function, for them to be invertible. They're saying though sometimes it is possible to restrict the domain of a function that is not one-to-one so that it will be one-to-one if you restrict the domain. So we looked at the absolute value function last time when we were doing the horizontal line test. And of course, we know an absolute value function fails when you do the horizontal line test. What happens with a parabola that opens up and down? It's pretty much going to be the same idea, right? Because it's a parabola that's opening up. So if you draw a horizontal line through a parabola, it's also not going to be one-to-one function. But think about it this way. What is the inverse of a square? A square root. So that means a square definitely has an inverse, but as a function, we know x squared doesn't work if I keep it on its original domain, which goes from negative infinity to positive infinity. However, if I restrict the domain of a square function and I only look at 1/2 of that parabola, I'm actually going to get an inverse function for it. So the idea is, if you have your x squared function, and just as a rough graph for it, we know this is what a parabola will look like. Now, if I draw a horizontal line through that, a horizontal line crosses at 2 different points, so I know I cannot create an inverse function from this. However, if I take the same function and only look at one side of that parabola, so basically just use this one arm instead of doing the other side also, which means we are actually restricting our domain and we're saying x can be 0 or greater than 0. So that means I'm only looking at the right-hand side of the domain. We're ignoring the left-hand side. So if I draw a vertical line through that, this is getting really annoying. I'm gonna have to talk to IT about that. I cannot keep doing this. So we know it's gonna pass the horizontal line test when I restrict my domain. Now, what is, again, the inverse of a square function?
Square root.
A square root function. So if I were to draw its graph and something like this would be the square root function. The idea here is, and I'm not sure I'm doing this right, but we'll think of this as the y equals x line. What happens with a function and its inverse is this y equals x line actually acts as the reflecting surface or your mirror surface, and they should look like reflections of each other with respect to this y equals x line. And if you actually go back to your handout, you can see I have a little graph in there. So this one here in the red is our y equals x squared function. This one here in blue is your y equals square root of x. And this green line is our reflecting surface, y equals x. They should be reflections of each other. This is true for all inverse functions. But the key thing here is I cannot use that entire parabola on my x squared function. I can only use it when x is equal to 0 and x is greater than 0. Other than that, if I keep the entire parabola, I won't be able to find its inverse function. So for some of these graphs that we're about to see, you will notice that we don't go for the entire domain. We have to restrict our domain if we're going to get these to work. And then they're just talking about, if you look at the ordered pair 2, 4 on the x squared function, which will be this point right here, 2, 4, it's going to become 4, 2 on the inverse function. So you should notice that your ordered pairs are definitely going to get inverted over here. Okay, so let's look at how we can look at the graphs of these examples here, number 17. So the original function given to us is f of x equals square root of x plus 2. Okay, so let's start by creating a table for this point. So what values can I use for x in this function? Yeah, so you can start with -2 and you can go to infinity, because again, since this is a square root, we cannot have any negative values in there. So the smallest number we can use in there is -2. So with -2, what kind of y value do we get? Yeah, you're going to get 0 because it's -2 plus 2, 0, square root of 0 is 0. What's the next number I can use? Yeah, you can use -1, which will give you, so -1 plus 2 is 1, square root of 1 is 1. Okay, good. Can I use 0? I mean, technically I can, but I'm not going to get a happy number. So what's the next happy number? Yeah, 2. Because 2 plus 2 will give us 4. Square root of 4 is going to give us 2. Give me one more.
7.
Yeah, 7 plus 2 will be 9. Square root of 9 will give us 3. Okay, we are going to find what the inverse function is, but as far as the graph goes, you can actually literally just interchange. What do you think? And we'll talk about what that equation will be, but literally just interchange your x and y columns, and you have the ordered pairs for your inverse function. So 0, 1, 2, 3 will now become the x values. -2, -1, 2, and 7 will now become your y values. Does anybody have an idea what the inverse function is for this guy? What do you think it should be? So remember, we switched the f of x, rewrite that as y. Then interchange your x and y variables. What should we do next?
Or not, square it.
Yeah, square it. So we'll square it. The square and square root will cancel each other out. And you're now left with, what's wrong with you? X squared equals y plus 2, and then to get y by itself, yeah, subtract your 2, and that will give us y equals x squared minus 2, which is your inverse function, right? These guys cancel out. So you guys have your grid. Go ahead, draw your graphs. So we've got -2, 0, -1, +1, +2, +2, and then 7, and +3. Something like that, and this is our y equals square root of x plus 2. So we changed those ordered pairs and we got 0, -2, 1, -1. We still got 2 and 2, and then 3 and 7. Something like that. And then just for reference, I'm actually also going to draw our y equals x line to show that these guys will look like reflections of each other. So that will be through 1, 1, 2, 2, 3, 3, and then down here. These guys are not cooperating very well. Okay. Hopefully you can get a little bit of a better image, but the idea is to make sure you're seeing that reflection with respect to this y equals x line. Okay, let's talk about the domain and range for each of our functions here. So let's start with the original function, which is f of x equals square root of x plus 2. What is the domain of this square root of x plus 2 function? Yeah, you're starting at -2 and you are going to positive infinity. And what can we say about its range? Yeah, because again, on the y-axis, it's starting at 0 and it's going to go up. So that's starting from 0 going to infinity. Alrighty, very nice. Now, obviously, we want to see what happens with the inverse function. Put this down a little. So that's going to be our f inverse of x, which is x squared minus 2. So what is its domain and range? So let's start with the domain here. Where are we starting? Yeah, because we're going from 0, we're starting right here at 0, and this function is only going to go to the right. So that's from 0 to infinity. And the range? Sorry?
-2.
Yeah, because this is where my inverse function is starting, is on the y-axis at -2, and it goes up. So -2 to infinity. So obviously you should notice that these guys are going to interchange with this. Like, questions on the graphing of these two functions? So you can basically see you're just creating the table for one function and literally just interchanging your x and y to get the ordered pairs for your inverse function. So let's take a look at what we've got next. Okay, here you've got square root of x minus 3 and then its inverse. So let me see what kind of graphs you guys come up with for number 18. And remember that -3 is outside the radical. It's not part of the square root of x. Okay, so what's our ordered pairs for the original table?
0, 1, 1. Oh, the -3, -2, -1,
3, -2,
-1, 0.
-1, 0. So of course those guys will now become the x here. What's the equation for our inverse function?
X squared plus 3.
X squared plus 3. Okay, so we start by adding the 3. X squared plus 3. Because you cannot do the square till you isolate your square root, right? So you actually need to add the 3 first and then take the square. So this is our f inverse function. Okay, so it should be, stop doing that. X plus 3 squared. Okay. So when we graph these guys, we should again have 0, -3. So down here, 1, -2, 4, -1, and 9, 0. You should actually not be crossing the x-axis till you hit the 9, 0. I don't know why this guy is not wanting to behave today. So this is our original function, x minus 3. And then our inverse function is starting at -3, 0, -2, +1, -1, +4, and then of course 9 for the y-intercept. It should look like that. And again, just for a reference, I'll draw my y equals x line. Obviously, my graphs don't want to cooperate because these are really sloppy graphs. Okay, but you should still be able to at least get the idea of that with the respect of y equals x as our reflecting surface. These two graphs are going to be reflections of each other. Now, what can we say about the domain and range for the original function? So for the square root of x minus 3 function, what's our domain?
It'll be 0 to infinity with the 0 included.
Very nice. Okay, very good. Range?
The range will be the -3 included to infinity.
Yeah, because this guy will go from -3, but it's only going to keep going up. So it's -3 to infinity. Alrighty, very nice. And then for the inverse function, when you're talking in terms of domain, where are we going? Trey?
Domain is -3 3 to infinity.
So you're going from -3 to positive infinity and range?
It's gonna be 0 to infinity.
Right, because again, you start at 0 on the y-axis and you go up. And obviously they should interchange from the original function to the inverse. So just be careful about how you came up with the equation of the inverse function, because it has to be x plus 3 squared. You cannot do the x squared first and then add 3 because you're looking at a completely different function. Now remember how we talked about transformations. You can still think about these functions using transformations, because when I have square root of x plus 2, that's actually telling me our graph moved 2 units to the left. So instead of starting at 0, 0, this graph moved 2 units to the left, and that's why it's starting at -2, which also affected its domain. If you look at the inverse function, x squared minus 2, that -2 on the outside actually tells me that was the vertical translation, which means our graph went down by 2 units, and that's why instead of starting at 0, 0, you're starting at -2. Additionally, remember what we talked about restricting our domain. So when I actually interchange my x and y table here, I am automatically restricting my domain, because you will notice I don't have this other half of my parabola on that x squared minus 2 function, because when I just interchange from my original to the inverse function, I already took care of that. Same thing happens here. You've got square root of x minus 3. So this minus 3 actually tells me our graph is moving down by 3 units. And so you can see instead of starting again at 0, 0, my graph starts 3 units down. And then with the x plus 3 squared, that plus 3 actually tells me my graph is moving 3 units to the left. So again, instead of starting at 0, 0 here, we move 3 units to the left. And again, we automatically restricted our domain, because again, I don't have this other half of my parabolas. So remember, with parabolas, you have to be very careful, because you cannot use the entire domain if you're going to find their inverse functions. Any questions on 18? Okay, so we're actually at the last part of this handout, which is talking about, instead of using the switch and solve method, can we actually find our inverse functions just mentally, just by looking at what operations are happening and how can we find its inverse. So they're telling us if an invertible function involves a single operation, so if it's just a plus, just a cube root, just a division, then it's going to be easy to write the inverse, because you just use the opposite operation. But what happens if you have more than one operation, right? So like we saw in this last example, you had the square root and you had the -3, right? So those are two different operations that are happening. And so here they're just showing you some examples of single operations. If you just have x squared with the restricted domain, then its inverse function is going to be square root. If you have 3 times x, so that's multiplication, its inverse is going to be division, x divided by 3. If you have x plus 9, its inverse is going to be subtraction, x minus 9. Single operation, finding the inverse function is easy. You've got more examples here in this little table. 2x will again become x divided by 2 since you're multiplying. Subtraction, the inverse is addition, so x plus 5. For a cube, the inverse is cube root. Now you should notice these two functions are like that negative x minus 9 function we have looked at. They are inverses of each other. So 1 over x is its own inverse, 1 over x, and negative x is also its own inverse, negative x. Okay, but what happens if you have more than one operation? So they are saying we find the inverse function by applying the inverse operations, which means plus will become minus, division becomes multiplication. So applying the inverse operations in the opposite order from the order which was given in the original function. So use the inverse operation in the opposite order than the order that's given to you in the original function. So let's take a look at this list here. And since it's not letting me write on the PDF itself, we're gonna have to use the notebook for this part. Okay, so our original function is 5 times x. This is a single operation, so what will its inverse be?
It's divided by
X divided by 5. Okay, not so bad. Part B, f of x equals x minus 88. What is its inverse? Yeah, opposite operation, x plus 88. So these were single operations. Now we're getting into 2 operations here. So you've got 3x minus 7. Okay, so let's think about this. If you have a number for x, let's say 1, what's the first thing you're going to do?
multiply by 3.
You're going to multiply by 3 first and then subtract 7, right? Which means the first operation that's happening is the multiplication by the 3, and then whatever answer you would get from that, then we would subtract the 7, right? So remember what they told us. Do the inverse operation in the opposite order, right? So that means when I go in the opposite order, I will inverse the subtraction of 7 first, and then inverse the multiplication of 3 last. So that's your opposite order. So start with x. So I'm going to reverse or take the inverse operation of the 7 first. So negative 7 will become plus 7. You're still doing the inverse operation. And then we multiply by 3 first. So divide by 3 last. So when they're saying inverse operation, which means negative will still become positive, multiplication will still become division, but you do it in the reverse order, in the opposite order. So since we multiplied first, we divide last. Since we subtracted last, we add first. Yes? Maybe? No? I'm going to take it as maybe. Since you guys are not really telling me anything. Okay, let's try with this guy. F of x equals 4 minus 3x. I actually don't like the way it's written. I prefer having my x values first. So I actually bring the negative 3x in the front and the plus 4 at the end. Which, I mean, even if you think about what happens with the x first, you can do it without rearranging it. My brain just likes to rearrange it. So again, the first thing, once I pick a value for x, again, I'm going to use 1. I will first multiply by negative 3. And then whatever answer I get, I'm going to add 4 to that. So again, we have to go in the opposite order. So for the inverse function, start out with your x first. That's always going to be your starting point. Now go in the opposite order. So where do I start first? And what do we do with the 4? Right. So since you're adding it in the inverse function, you are going to subtract it. And then since we multiplied by negative 3, we're going to divide by negative 3. So you can leave it like that. You can bring the negative in the middle and have x minus 4 over 3. Or you can bring the negative to the top. But if you do that, put it in parentheses. So any of those 3 options are okay. You want to leave it like the first one, that's fine. Whatever seems to be more comfortable for you, okay? Ladies, you gotta stop talking. You're talking a lot.
Oh, sorry.
Okay, what do you think is going to happen on E? Yeah, E.
You're multiplying by first.
Multiplying by half first,
And then subtracting 9.
and then subtracting 9.
We're going to add 9.
Okay, so for our, again, start with your x, and yes, we're going to add the 9 first. Now multiplying by 1/2 is the same as, yeah, dividing by 2. So multiplying by 1/2 is the same as dividing by 2. So if you're dividing by 2, that means we will multiply by 2. So that means, if you're thinking of this as multiplying by 1/2, you can also think of as dividing by 1/2, which would still clean up into multiplying by 2. So again, I'm going to let you figure that one out. Let's clean this up. What do you get? 2x plus 18. Okay. For f, you are given f of x equals negative x.
Is it negative x?
It is negative x. Because here's the math if you want to think about it. Doesn't matter if you think about x as being multiplied by -1 or divided by -1. So to keep it easy, let's say we're multiplying x by -1, which means its inverse would be taking the x and dividing by -1, right? This multiplication goes as an inverse with division, you're still going to end up, and if you did this as division, that guy would become multiplication. So either way, negative x is its own inverse function. Okay? I was like, what comes after f? It's g. Okay, what do you guys think for g? What should we have? Cube root of x, and then on the outside we have -9.
X plus 9 cubed.
Okay, let's see. So the first operation happening here is the cube root, because that's what we would do first. And then whatever answer we got from here, we would subtract 9 from it. So again, going in the opposite order. Its inverse function. Start with the x. So if you're going in the opposite order, what do we do first? Add the 9. And then since we're taking the cube root, you're going to cube it. And of course you cube the entire thing, just like we multiplied this guy, the entire thing by 2. You take the cube on the entire function. So you will actually get x plus 9, the whole quantity cubed. Okay, let me see what you guys come up with the last two. Space in that. So there's 3 operations happening here on H. So take your time, see in what order the operations are being performed, and then go in the opposite order from that.
Yeah.
Okay, so the very first thing that's happening with the x is x to the third, because that's the part we would solve first. then whatever answer we get, we would multiply that with the 3. And then the very last thing we would do is subtract the 7. So when you go in the opposite order, you're actually going to end up with adding the 7 first. Since it's multiplication, that means you're going to have division. And most of you guys did fine at this point, but some of you actually kept the third power. So since it's to the third power as the exponent, its inverse operation is of course going to be cube root, which means you're going to have cube root as the last thing, which means it goes on the entire fraction. Okay, so just be careful with that little operation at the end. And then for I, you are given the original function as 2/3 x plus 6. So there's actually 2 ways that you can think about this problem, and it's up to you how you want to look at it. So you can think about as the x being multiplied by 2/3. If you want to break it up into 2 pieces, you can also think about it as x being multiplied by 2, and then whatever answer you get is being divided by 3. So you can actually break it up into 2 operations if you want. And then of course the very last thing is adding that 6. So when we go in the reverse order, that means you would start out with the x. Since 6 was the last thing that was added, 6 would be the first thing that's being subtracted. And then if you're looking at it as 2/3 is being multiplied, remember that means you are actually either multiplying by flipping that fraction, which actually takes care of 2 being multiplied in the first one becomes 2 being divided in the inverse. 3 being divided in the first one means 3 is being multiplied in the inverse. So you can do this if you're looking at this as 2 steps. Now, if you're looking at this individually, obviously you're still going to get the same result. We start by subtracting the 6 first. Since 3 was being divided, that means 3 is being multiplied. And then since 2 was being multiplied, that means 2 is being divided. And like I said, you're still going to end up getting the same result. But if you want to break it down into multiple steps, you can. Now clean that up. So you've basically got 3/2 in the front, x minus 6. If I clean this up, I will have 3/2 multiplied with the x, 3/2 multiplied with the 6, which will be 3 times 6 is 18. 18 divided by 2. You're going to get 3/2 x minus 9. Obviously, I will accept on the exam if you leave it in that form because you obviously have the right format there. As far as my math lab goes, you will have to see if they want you to simplify or not. I'm not sure what my math lab does on that. Now, let me tell you something. The mental process of finding inverses is okay unless you run into this example. Number 13. Does anybody remember what that inverse was for number 13?
So it's 5x minus 3.
5x plus 3 divided by x.
Yeah, 5x plus 3 divided by x minus 1. I mean, you can fiddle around with it. I haven't been able to figure it out how to do it mentally, but you might be able to. For this one, I highly recommend sticking to the switch and solve method. Now, switch and solve method would obviously work for all these examples that we did at the end. So when in doubt, if the mental method seems like, okay, I'm confusing my order or whatever, just go to your switch and solve method and it's going to work every single time. So questions on solving your, finding the inverse functions. Okay, really quickly, I just want to show you what 2.6 was about. I think it's an important section, but obviously that's not part of our required section. So this is where they actually talk about different types of variations. So you have direct variation, which basically tells us if one quantity is increasing, then the other one that depends on it will also increase. And you can see that's your basic direct variation equation, y equals k times x, and k is what we call as your constant of proportionality or variation constant, proportionality constant, whatever you want to call it. Depending on the textbook, they'll have a little different name for it. So in this example, we're saying if the cost of a house is $64 per square foot, then you're basically looking at a linear function where the cost depends on the square footage of the house, right? So the larger the square footage of the house is going to be, the more expensive the cost of that house is going to be. Obviously, the smaller the square footage will be, the less amount you'll end up paying for that house. So that's the idea behind a direct variation. If one value grows, the other one also grows. Then you have inverse variation, which obviously means if one value will increase, the other one should decrease, or if the first one is decreasing, the second one should increase. And I really like this example because we are talking about just a regular Boeing 747 airplane and comparing that to the Concorde, which of course they have decommissioned the Concorde like more than 15 years ago or so. But the idea is if we're talking about making the trip from New York to London, which is a 3,470 mile trip, they're saying with the Boeing, you're averaging a speed of 675 miles per hour. And they're saying it's taking you about 5 hours to get there. With the Concorde, you're looking at almost double that speed, right? 1,350 miles per hour, which means you should get there a lot quicker in 2.5 hours. You're going to make that same trip, that same distance. So in this case, the idea is when the speed goes up, the time goes down, right? When the speed goes down, time goes up. And I always use this example with my students because I've actually done this. When I lived in Kentucky, my friend lived in West Virginia, and this was like a 6-hour drive. And every time I would try to see how fast can I go without getting pulled over. And I have actually done 90 miles per hour on this journey, and I've maybe saved 10 minutes. Literally, I did not save a huge amount. And this was with no breaks, right? No stopping for gas or food or anything. And so I was like, this is so stupid because I saved maybe 10 minutes at the constant headache of looking all around me, every mirror, every crevice on that highway. I was like, is there a cop car there? Is there a cop? But I just wanted to see if I could do it. And I was like, this is so stupid because now my head hurts. So don't try it. This is my disclaimer. You do not save time unless you're a Concorde flying at 1,350 miles per hour. And then of course you also have other variations like joint variation where you will have more than 2 variables. So in this case, we're actually saying your one variable is depending on 2 more values. And this is your talking about how you can have in this case, we're talking about the length and the height, but you can think about area of a rectangle, right? Length and width is going to help you with the area. So here we're talking in terms of the cost of the fence is based on how long and how high it is going to be. Now your combined variation is where you have actually direct and inverse variation together. So one quantity goes up, but the other will go down. And we didn't really have a good example to show you from that. I think this guy might be the closest one that we get to. Yeah, direct and inverse. So here we're saying in terms of the time required to process a shipment of oysters varies directly with the number of pounds. So of course, the more pounds of oysters you have, the longer time it's going to take, but inversely with the number of workers, right? So the more people you can get to help you with that process, then the less time. So more pounds, more time, but if you can get more workers, that means you're going to take less time. So variation A lot of examples we do are based on inverse and direct variation. I mean, think about y equals mx plus b. If you are keeping that b at 0, that's a positive slope. Your line is going to go up. If I make that a negative slope, then I'm looking at an inverse variation because one value is going up when the other one goes down. So we use variations in a lot of these examples that we normally do. But, of course, we just don't think about it as in terms of variation. So this was just a quick overview. You're not going to have exam questions on this. There's no homework on that. But you should at least be familiar with the idea of variation. All right, so we are done with chapter 2. I've already made the changes in my math lab, so your homework is due on Monday, I guess whenever the class ends. And you guys are coming prepared to take your chapter 2 exam on Monday, all right? If you guys have any questions, I will be here probably for another half an hour or so, but then I'll be here tomorrow all day. So if you have any questions, just let me know. All right, guys, have a wonderful day, and I will see you on Monday. Enjoy your weekend.